Okay, students, this is session number 28 on industrial metallurgy. These are the table of contents. We will now discuss about hypoeutectic bismuth cadmium alloys, their equilibrium cooling, and we'll show some important microstructures during the course of their slow cooling, that is equilibrium cooling. Uh, we discussed it in the last session that on the basis of the eutectic reaction, the type 2 alloys, or you see the bismuth cadmium alloy series can be categorized into three classes of alloys. The metallurgically most simple alloy is the eutectic alloy, and in some lectures to come now, I'll start referring this term that eutectic alloy is the alloy which shows the eutectic reaction completely. Now, what does that mean? That means, see, whenever any alloy, whether it's a hypereutectic alloy or a hypoeutectic alloy, when they'll show the eutectic reaction, they'll also show it completely. But it is only for the eutectic alloy that we write down that for a eutectic alloy, the eutectic alloy is one which undergoes the eutectic reaction completely. It has a different connotation. It has got a different meaning. See, what we try to emphasize upon by using the term "it shows the reaction completely" is that it only has the reactants and then the products which come or which are used by the reaction. You see, in the eutectic reaction, when we reach the eutectic temperature, the eutectic alloy has got 100% liquid phase in it. And if that liquid phase is of eutectic composition, obviously that liquid phase is of eutectic composition only. So the entire thing that is present in the eutectic alloy just before the eutectic temperature is what will participate in the eutectic reaction. Means the entire thing would act as a reactant for the eutectic reaction. There is no other phase present. As a result of that, what would be present just below the eutectic temperature would be only those things which have come because of the eutectic reaction. That's the eutectic mixture. But in case of a hyper eutectic alloy or a hypoeutectic alloy, you will see that when the alloy is just during cooling on the verge of reaching the eutectic temperature, above just above the eutectic temperature, the alloy does have liquid solution of eutectic composition in it, but that's not the only thing. Along with that, some other thing is also present. So just after the reaction, eutectic reaction has got formed because of the liquid solution of eutectic composition, but that's not the only thing. There is some other phase also that continues to exist. So for this reason, we say that it's only the eutectic alloy which undergoes the eutectic reaction completely. Means just before the eutectic reaction, it has got only those phases in it which would be used in the eutectic reaction, and thereby just after the eutectic reaction, it has got only those phases formed in it. Those have been formed due to the eutectic reaction. Okay, by the way, now let us discuss about the hypoeutectic alloys. We have already said in the last session, any alloy which contains from 0 till 40% cadmium is a hypoeutectic alloy. And now we'll discuss, taking one of the cases, the equilibrium cooling of a hypoeutectic alloy. Now, for your reference, again, I have written down the eutectic reaction, liquid solution of eutectic composition. If it is present, it forms two new phases called the eutectic mixture. Specifically for bismuth cadmium alloy system, this liquid solution or this liquid phase has to be a liquid solution of this composition. And if this is present at the eutectic temperature, sorry students, this should have been 144. By mistake, this is written as 727. I'll correct it. And so if you have liquid solution of eutectic composition during cooling present at the eutectic temperature, the liquid will transform into pure bismuth and pure cadmium. This would be 60% by weight and this would be 40% by weight, and this is the eutectic mixture. So let's now take the case of a hypoeutectic alloy and see what microstructural changes take place during its equilibrium cooling. For illustration, we have taken a hypoeutectic bismuth cadmium alloy which is containing 26% cadmium in it, and remaining is bismuth. So what I'll do, I'll mark this composition. I'll draw a straight vertical line, very high temperature. We start discussion on the equilibrium cooling. We have taken this 26% nickel alloy at a very high temperature corresponding to point A. Only one phase exists in this alloy. That phase is liquid solution of copper and of bismuth and cadmium. The chemical composition of the liquid phase is the same as is of the alloy. The weight of the liquid phase has to be 100% by weight because it's the only phase that is existing at the moment. We start cooling the alloy under strict conditions of equilibrium cooling, very slow rates of cooling. No change occurs in the alloy till we have reached a temperature corresponding to point B, and this happens to be the liquidus temperature of this alloy. On reaching this liquidus temperature, the first glimpses of the solid phase are seen. See, pure bismuth appears slight pinkish in color. So this solid phase I have shown for you in the pink color. So the first solid phase appears in the microstructure. If you are interested in its chemical composition, draw a tie line from here, and what you would see is that this solid phase is of 100% bismuth composition. So I've written over here solid is of 100% bismuth composition. You need not apply, though this is a two-phase region that is on the liquidus line, but as a general rule, we generally don't apply the lever rule over here, and simply we can write that 99.99% is still liquid and 0.01 is the first trace of the solid that has appeared in the microstructure of this material. And the chemical composition of the liquid would have slightly shifted from this 26% and would have become about 26.01 or 26.1 cadmium. So the same has been written for the liquid phase. Now it is of about 26.1% cadmium. The composition had to change because now a newer phase has come out of it. Then as the cooling proceeds and we have gone down from temperature TB to a lower temperature TC, again you have shown the microstructure. We are still in a two-phase region, liquid plus bismuth, so you have liquid solution and pure bismuth solid in the microstructure of the material. But what's important is that what's the chemical, not even the chemical composition. You would note a strange thing over here. Generally the critical nuclei are shown to grow into the form of dendrites, right? Because in most metallic systems, the solid phase that is growing is something which is highly metallic. But see students, this is an exceptional case. This is a type 2 system. This is a system where the two elements are drastically very different from each other in the chemical nature. And generally a type 2 system will get formed when one of the constituent elements is very metallic, the other is very less metallic. The same is the case here. Bismuth, out of these two elements, bismuth and cadmium, is a less metallic element. So here, actually you are showing the growth. This solid phase is nothing but pure bismuth. And since pure bismuth happens to be a less metallic thing, we cannot show it through dendrites. Though actually it would be growing like dendrites, but as a convention in metallurgy, anything which is less metallic or not metallic is not to be shown in a schematic representation, is not to be shown through a dendrite, because dendrite, no sooner you speak out dendrite, it means grown solid phase, but solid which is highly metallic. So here, because a less metallic thing has grown, we generally use this square or cuboidal shape. So this is one characteristic that you must know. Then what's the chemical composition? The two ends of the tie line would give you the chemical composition. I have marked for liquid it's 30% cadmium. For solid it has to be 100% bismuth, because we are assuming that what is coming out as a pure metal. For hypoeutectic alloys, that pure metal is bismuth. For hypereutectic, that pure solid phase would be pure cadmium. So whenever you show solid phase over here, it ought to be bismuth only. Importantly, when we reach point D at a still lower temperature, the solid phase further grows. And now you see we had started with 0.01 solid, at the liquidus temperature. Then we reached 13.33. Now we have reached about 35, right? And then students, very important temperature, we are just on the verge of reaching the eutectic temperature 144. So its point D is at a fraction above 144. So I have drawn the microstructure over here. What I see is I have this liquid solution of 60 bismuth, 40 cadmium. And what is this, students? This is the eutectic composition. How much of liquid solution of eutectic composition do you have? Through the lever rule, I have found out it's about 65%. What would happen after a fraction of a temperature drop takes place? This entire liquid would undergo the eutectic reaction and it would form pure bismuth eutectic and pure bismuth, pure cadmium eutectic. So this entire, just when you reach here, and that I have shown just below the eutectic temperature at point E. So at point E, this entire liquid will transform to eutectic bismuth plus pro-eutectic bismuth. And then you had this bismuth which was already there without the eutectic reaction, before the eutectic reaction. So this bismuth now we'll start referring it to as pro-eutectic bismuth. So this bismuth that was already there, this, and the maximum was just above the eutectic temperature. This is called pro-eutectic bismuth. And there is another bismuth that has just got formed because of the eutectic reaction. And there is this blue region is eutectic cadmium, because pure cadmium gives you a slightly blue color. So I drew them in a slight blue color for your better understanding. So if you look at the, and importantly, no change now would take place in the microstructure of the material when you go from when your temperature drops from TE down till 0 degrees centigrade, or maybe somewhere over here at room temperature. So the same microstructure that you have seen over here would be here, here, even here, right? And in this microstructure, somebody can ask you, what is the total amount of bismuth present? Total amount of bismuth present is this plus this. Pro-eutectic is 35, eutectic is 39. Or otherwise, what you can do, you can draw the tie line in this region and you will get the total bismuth through the inverse lever rule as 39 plus 35, somewhere around 74%. And similarly, if you again apply the lever rule over here, 100 minus 74 would be 26, would be cadmium, and all cadmium that we have in this microstructure is eutectic cadmium. So if somebody asks you what amount of pro-eutectic cadmium is being seen in this alloy, 0. There is no pro-eutectic cadmium. Similarly, if somebody asks you that what is the total pro-eutectic cadmium, maximum pro-eutectic cadmium, see any, a pro-eutectic bismuth. See, any bismuth which got formed in this region is pro-eutectic or primary bismuth. All that got formed isothermally through the eutectic reaction over here is eutectic bismuth. What you see over here, if you apply the lever rule, is the total bismuth, which contains both pro-eutectic as well as eutectic. So students, I think this, with this discussion, we bring this brings us to the end of discussion on the equilibrium cooling of hypoeutectic bismuth cadmium alloys. In the next session, we'll take another example, but now of a hypereutectic alloy, and then we'll discuss that how is the microstructure evolution different in case of hypereutectic bismuth cadmium alloys. Thanks for being there and listening and watching this presentation. Thank you so much.